Let's continue with secondary structure prediction. What we got to, the point we got to on last week was that if you look at segments of consecutive residues and you use those, the information contained in those segments, to put that into a machine learning device to predict what the secondary structure of the central residue is. So for instance, you predict the middle finger secondary structure and you use the two fingers on either side, the information from the two fingers on either side as input, then what you essentially get is a method that is as good as everything else. Gets sort of a Q3 of 62%. That is sort of the match state. So how many of the residues are correctly predicted in either of the three states, HEL? 62% roughly. And when we look at what fraction of the correctly predicted residue is helical in red, what fraction is beta strand in blue, and what fraction is other, we see that most of it is white. So most of the residues that are correctly predicted are neither helix nor strand. We observe that in fact the same observation or the same distribution is found in the database. So the same distribution of helix strand to other residues. And the suspicion was that in fact the machine learning device did not learn, not because strand interactions are less local than helical interactions, which they are, but possibly only because there are fewer of those in the database. So let's just overrepresent them, was the idea. Represent them equally and then you get an equal distribution. Again, the way you overrepresent them, typically the machine learning device, the neural network, picks samples at random to change the connections. Again, I had sort of this rough idea of the landscape. If you imagined, so the free variables are the connections, and if you sort of roughly presented the space of connections here of all the junctions, and that is the error landscape, then there is some function here. And essentially training means you go downhill. Going downhill means that for every sample you present, you find a step toward reducing the error. Change the connections, the junctions such that the error is reduced. That's the simple algorithm. And in this algorithm, you choose your samples for training at random. Why do you choose them at random? Why do you not take residue I plus 1, I plus 2, I plus 3? Why do you choose them at random? You could, yeah?
Because you hope that they are uncorrelated in that.
Sorry,
you hope that they are uncorrelated in that.
And you know that if you pick them at random, they are uncorrelated. True, that's absolutely true. That's correct. But why do you want them to be uncorrelated? Any idea? I mean, sort of in a visual sense, this curve suggests something. If they were too correlated, what will happen? Too correlated means you pick samples that are specific to one particular protein, I plus 1, I plus 2, I plus 3. So many of the subsequent or the subsequent steps of change depend on something that is correlated to what you did before. That means that you give the system a push in one particular direction. The system in the push of one direction, you increase tremendously the probability of freezing in local minima. You do not find a solution that is good for all the samples that you're going to present, but you find one that is good for whatever your local correlated environment is. Now that means that you sort of give a push in a certain direction and then you give a push in another direction. You give big pushes in wrong directions, and that leads to worse classifications. So you can just do it, and the result typically is that the performance of these systems, if you do that, is much worse. So that's why you present them at random. Now when you present them at random, this balanced prediction here means if you present at random and you have that distribution in the database, then ultimately say this white one here would be 50% of the pie, then ultimately that means you would pick an other state 50% of the cases, right? And that's the way you get this performance here. If, however, you enforce that in that 33% of the cases are going to be white, 33% red, and 33% blue. So each of the three states is equally distributed at one particular move step. So you pick 3 samples at random from each of these states, and then you make a change. This is still uncorrelated, because these 3 Samples are taken from different parts of the space. Now, again, it means that you overrepresent the underrepresented state. So you sample this as 33%, while in the database it's only 20%. So you push more copies of this. Again, the result is that it's very balanced. Now, that means that we can do much better for beta strand, and it has nothing to do, that most methods get beta strands wrong, has nothing to do with the fact that beta strand correlation is done local. But there is another issue now. We have talked about the sparse cording. I'm sorry. There's another issue. The other, have we talked about this? No, we haven't, right? The segments, sorry? I'm not, I believe I thought that I looked at the video, but since there was a slide in here that was clearly wrong, I'm not sure. Anyway, so I mentioned that typical methods predict segments too short. That means they say my predicted helix has 2 letters, 2 HH. Or my predicted beta strand has 1 letter, E. And for a user that is not very useful, because you know as a user it has to be at least 4 residues long. It has to be HHHH if it's a helix, at least. So now if you see 2 H's predicted, you don't know what to do. Does that mean that you wipe them out because 2 residue helix doesn't exist, so there's nothing predicted there? Or does it mean that the method actually should have predicted 4? Okay? Which way do you go? One way in which you could do that is you could sort of follow the probability and simply sort of put some intelligence into the system by saying, well, I know helices are at least 4 residues long. I have a seed where I predict HH simply because at that particular position the signal for H is the highest. No, I have to ask, do I extend in that direction or that direction? And I will decide the extension according to if the probability, if the second strongest prediction is also a helix. Maybe in these 2 directions the strongest prediction is the other state. But maybe the second strongest is actually a helix, and then I extend. But then this is one way of doing it. The trouble is you begin to optimize or introduce a lot of parameters. How many steps are you going to go? How low is second enough? How different does it have to be? Is it okay if the first has 0.8 of the probability and the second has 0.1 and there's a helix? Do you take it then? Or does it have to be more similar? So that's the downside to it. There is a more generic way of doing it. And ultimately, let's just repeat what I said. That's sort of an average predicted, that's an average observed, so much too short. And it comes from the fact that the neural network, because it takes out the correlations in order to it picks the samples at random. By picking the samples at random, it takes out the correlations, and that means the system has never learned that helices are at least 4 residues long. So now we have a part where training at random is a bad idea, in some sense. We have to do it because otherwise the performance is too poor, but we lose this correlation signal. How could we put that correlation signal back into the system? We could try to sort of locally pick I and I plus 2 plus 3 or plus 4 or something like that, but that doesn't work. So we tried that. Could have worked, didn't. What else could we do? Yeah?
Is there a question?
Yes?
Why, if we don't train at random, but if we oversample the examples that we can predict well, so that we have a better prediction or better accuracy for each class? Why isn't the overall accuracy better?
So the question is, I said that if you trained I plus 1, I plus 2, I plus 3, so just in the order in which you see them in the protein, so you completely allow the correlation, then the performance would be worse. And the question now is why? And the very clear answer to that, I cannot answer that question. Because people have tried both ways because they cannot clearly answer your question, okay? Now comes the rationalization of an observation that I cannot completely answer why. I do not understand machine learning well enough to give you the answer why. But the impression that we have, why, is, again, what you do if you train along the line of an entire protein. What you do is you sort of optimize this space here along the line of one particular protein. in your entire set, say are 10,000. And you pick one to decide a long part of the step. It's only 1/10,000th of the training, that is true, but in this 1/10,000th of this training you get into a very correlated direction. That's the point. So you learn everything somehow from one protein. And that tends to lead to overtraining, because in order to train on 10,000 you need a network that is big enough, or a machine learning device that can handle 10,000. That means that if you sort of go 1/10,000th of the steps of one protein in a particular direction, then you overtrain in that particular direction. Yes, you will correct for that if the next one comes along. But that means you're sort of, rather than have a smooth training that sort of goes into directions that are somehow good for everything, or at least not bad for everything, because you get another step again, you have 100, or whatever the length of the protein is, 100 steps into one particular direction. And that tends to simply go wrong. You do too much overtraining. And presenting protein number 2 corrects for the overtraining. The benefit of, in fact, seeing what the correlation to the other residue there is, you lose too. Because the moment you present the second protein, you lose the benefit again, because you present the correlation only for the second protein. And the strongest signal that you give is not to learn that I and I+1 is correlated. What you learn is protein 1 and protein 2, they are different. So you learn the wrong thing. That is the rationalization. It's not an answer to why. I cannot give you a why. Any other question at this point? So then again, the question comes, how can I put this correlation? The way we have to train these systems, it cannot learn that a helix has to have a minimal length, because I cannot allow the correlation between adjacent training samples. So how could I still put this correlation into the system? Any idea? Yeah?
Digital matrix contains biological data.
Well, we are training on biological data, right?
For example, like a score matrix, this amino acid is H, what is the probability this is H?
But okay. So if we did that, if we put a probability of this particular amino acid is in an H. Remember I said the first generation methods, they got to a performance of 50 to 55%. Q3 is about 50 to 55%. Oops. The one that I'm talking about now is the first generation here. The second generation, Q3, is about 62 that I have here. So if I now put back a signal from that accuracy, most likely I'm going to make things worse. So most likely I'm not going to pick up the correlation. Instead, I'm going to reduce the Q3. So in principle, if we had a method, here's the other reality. All of these methods that looked at probabilities, even for segments, they also did beta strand very poorly. So they did not pick up the correlation somehow. And the segments, not beta strands. So what could we do? So we cannot use, there is no method there that we can use, because they all suffer from the same problem. We need to invent something new. Or needed. It's a few years ago that this was invented. So now it's on the internet. But do you have any idea how to do it? I mean, invent some method that would somehow do it. There are different ways of doing it. So you somehow want to bring the correlation into the system, but you do not want to train such that you train on correlated samples. How could you do that? Some of you have most likely seen deep learning methods. For those of you, LSTM is sort of the key word that sort of has a similar idea behind it. Yeah?
Or what about convolutional neural networks?
Well, that's sort of what I'm saying, right? But convolutional network itself is not alone the solution. You need something. So you need to feed it back. Okay, let's on that level of convolution. Yes, that would do it. So you need to somehow find a system into which you put the information of what you did in the step before back into the system. One way of doing that is this one here. Convolutional networks, I'm not going to show you an example of that, but the simplest way in which you can do that is you take the networks that I showed you before, where amino acid is the input here, 13 consecutive residues, amino acids, 3 output units. And say that is the prediction for the residue V. Now you slide it forward. You move this sequence, you thread the sequence through your network, and you predict for the next, the P, and then you predict for the next, the A. So now I have sort of 3 consecutive residues. The sequence reads VPA for this particular protein here, and the secondary structure is EEH. And now you simply take the prediction of this first level network, that is input sequence, output secondary structure. You take the secondary structure that this first level puts out, and put it into a second level network. Again, now you, instead of having 13 times 21 input units, you have simply 3 input units. So 3 and 3 and 3. I draw 4. Why do I draw 4? It's not a bias. No. We need a 4th unit. We have 20 amino acids. Nevertheless, for the previous method, we used 21 input units. Why? Do you remember that? Yes?
Can you produce a gap?
Not for the gap. No. Oh, maybe I didn't say it. Then I forgot to say it. This is bad. So good that I stumbled over it here. Say my sequence were VP. A, G, say, okay? And so say my neural network that I use for secondary structure prediction, this first or second level, has only 3 input units of, and I predict what the central input unit should be. Say the central input unit is the A. I predict the secondary structure for the central input unit. So my 3 window thing uses 1 before and 1 after. So then I slide it over 1. Now the P is in the center. But what do I do if the V should be in the center? You see that if the V is in the center, there's 1 above it. That is not an amino acid. In that sense, you could call that a gap. But ultimately what it codes for is no amino acid. It's end of protein. Right? It's not quite the interpretation of a gap. It's something else. It's end. And so you see that on this side on this side you have the same issue. If this one here is going to be the central one, you have one of these spacers in the end. And that's the same thing why you need 4 instead of 3 as input units here. You need a spacer unit. Right? Is everybody clear about this second level network? Yeah?
The very first layer, how many neurons do we have?
So this is really, in this particular case, what I show. In this particular case, we have a window of 3 consecutive residues, and we predict the secondary structure for this one. We have actually 4 plus 4 plus 4. 3 times 4, 12. The other ones, so this is a completely separately trained network, okay? This is what we talked about so far. We trained this network here. We have, in this particular case, we had 13 times 21. 20 amino acids, so each of these inputs, so we have a window of 13 consecutive units, or 13 consecutive residue positions. So you look at the degree to which I is influenced by I minus 1, minus 2, minus 3, so until minus 6 and plus 6, right? That is the input to this one here. And since every residue is coded for by 20 amino acids plus a spacer, we have 13 times 21 input units there.
But do the numbers match? Like, are there here 30?
So, just because I cannot draw, so if I would have drawn, instead of 3 here, 13, it is more difficult to see. So I call it a window of 3. Ultimately, actually, so the second level here, you can even do more because the input space is so small. So you have so few input units that rather than windows of 13, you could use 21 even. And it actually pays off. So longer windows are better. It's just for me impossible to draw it here. Or I cannot give you. So for me, as the one who has done this image here, the question was, on the one hand, I want to sort of give you really the detail where you can count. And on the other hand, I want to give you the overview. And for that, I need a window of 3. Yes?
Can you maybe run through like an example of this first?
Yes, so let's begin with this part first. This is exactly what we did last time. So we have an amino, and I believe out of what I thought mistake. So we have 20 amino acids, 1 for spacer, 21 units, and we have 13 consecutive of these 21 units. Consecutive means, so my sequence in the protein is D, R, Q, and so forth, right? This is my sequence, and I simply take, in this particular case, 13 consecutive residues, residue I plus 1 plus 2 plus 12, 13 consecutive residues I take out of my protein, and I predict, that's my window, and I predict the secondary structure for the central P here. Happens to be a P. And that is why the output here is 3 units, HEL. Helix, strand, other. So much, so clear. That's the part that is clear for everybody. So I simply train this entire network. And when I train this entire network, I have the issues that I talked about, that segments are too short. And, whoops. So now, I take what I trained before, and train a new network. This new network, as input, has the prediction of the old one. So for every single residue in every protein in my training and testing set, I predict the secondary structure. Here, in this example shown, I had predicted such that the V is in the center of this window. And the center of this window is a P, and it predicts an E, and it predicts an E. And here of the center is an A, and it predicts an H. Okay, that's the example here. Yes?
Why do you use 1 and not 2 spacer?
Oh, you mean one for the end and one for the beginning? Well, the assumption, this is a very interesting issue, and I don't want to get too much into it. So you can, in fact, there is, ultimately your idea is that there's some difference between whether you're on that end of a protein or that end of the protein. And there's a truth to that. So this Y issue is again somehow a similar Y issue as this one here. I cannot quite answer it. Typically machine learning, what you do is you try them both and see what works. It's what I did. And it turns out that using one worked better. But biologically there is a difference between the two ends, and you can put that information back into the system. But now the Y is a little bit better explained. So if I added one more unit for that, I would put too much emphasis on the difference between the two ends of a protein. So I would over-represent the biological reality in some sense. So that's why it's better to here have only one, and then put the other information into something that is less information content.
And what is used as the spacer amino acid?
Sorry, what is used?
Is there a certain amino acid that is used as the spacer?
No, so this spacer is just no amino acid. So it's just if we I'm sorry for the going back and forth in my presentation, but if we look at this presentation again here, in the sparse coding, in the one hot, as you call it, people call it today, in the one hot encoding, essentially one of these 21 units is on. All the others are 0. And that is simply the last unit that is on whenever this unit is the end of a protein. It does not code for any amino acid. So there are, I said, let's not get into that. Yeah?
Can you also kind of assume that maybe like half of the input strand is like the end?
Sorry?
That half of the input strand is the end, like whatever, like you just have a part of the protein, right?
So what would you do if somebody cut your protein into peptides? Is that what you're asking?
No, it's like I don't understand why you need like this endpoint, because why would you include it?
Oh, why would you include it at all? So, okay. Very often, again, in machine learning, the answer to these why questions is try them both and see what it is and then rationalize why what you observe is true. You could also code for the end by saying, rather than introducing a 21st unit, you could simply make them all 0. So you would have a vector that, because if your center is the D, if you have a window in which, so in this example here, if your center of my 3 window is supposed to be the V, then before I don't have an amino acid, right? And I could simply code for that by saying, well, I have a vector that codes for 20 amino acids, and if none of those amino acids is there, this vector is 0.
But if the span is like 30, right? The center, everything above.
But there's,
Everything above is the point.
So, well, so some proteins, so you could, here's an alternative way in which you could do it. You could just leave them out and could say, I don't predict. So since my window is 13, I only throw away 6 residues at the beginning and 6 residues at the end. When you look at a protein that is 100 residues long, 6 on either end, throwing away 12 residues of 100 is 12%. Right? This is something. And maybe you can do better than throwing it away. Oh.
Sequence, which is like 120 long, right? And you kind of usually take like 30 residues and then predict the structure of the middle residue.
Yeah.
That's correct. So if I want to predict like the structure of the residue in the 120 sequence,
Yeah.
then as an input I would have like all the upper parts to be the point, right?
No, so I'm not sure. So I have to admit I don't understand your question, but I suspect that I have not clearly stated what you do. So you have this 13 consecutive residues. That predicts. So let's just have, instead of 13, let's have 3. Let's assume I have a protein of 5 residues, that is 5 residues long. So we begin with an L here, LVP. So my 3 thing, the first window will be this, where L is in the center, a spacer on top, and the V. The second will be this. The third one will be this. So I slide my window through. In fact, I slide the window through 5 times for this protein.
Okay, but if your window would be now like 5, you would have spacers like the first and the second.
You have just, the longer the window, the more spacers I mean, the more residues have spacers. It's still your 21. Yeah? Is that clear now? Yeah?
So these 3 output neurons became 4?
Sorry, they're not output neurons. So this is the input. And simply because I cannot sort of play this, I don't have 13 fingers, and I'm too lazy to put long proteins here. I just think, yes, they are 3. Oh, you mean for the next level? Yes, they become 4. Because they become 4, but now let's first make sure that we are all on the same page for this slide before we get into the second level. I now realize that I have not made that very clear here. I apologize for that. So that was the reason why actually the slide is in here, and I thought it was incorrect that it was here. Again, so we slide, if the protein has n residues, we slide whatever window size we have, shown here is 13, we slide that n times through the protein. So every protein for any W, if the length is 13, so W equals 13, for any W, completely independent, you always will have n with these windows. Okay? Is that clear?
What's
The length of a protein. So if you have a protein of n residues, every residue will be sort of part of one of these windows. Again, you could do that differently. In deep learning, you, for instance, typically code today the entire protein. But more about that on Thursday. Okay. And then now, indeed, the 3 units from before become 4 for each residue because there's no spacer used. Again, in the same, previously there was 20 that became 21. Now it's 3 that become 4.
Weren't we also using 21 in the previous slide?
Yeah, in the previous slide we have 20 amino acids, but they lead to 21 input units because there is a spacer added. And the same spacer is added here. So this unit is only for cases where, again, if my first window here reaches beyond the end of the protein.
Yeah,
Then,
wouldn't it also be of interest to have a prediction for the spacer also also on in the previous?
Yeah, we have. Oh,
We only have 3.
no, but what do you mean a prediction? So I'm not predicting, so I will not move the window, I'm not entirely sure what you mean by prediction. So I will not move the window to the outside of the protein. So the center will never be outside of the protein. The central residue is always predicting some secondary structure because it must be a residue. We cannot predict a secondary structure for something that doesn't exist. For a spacer, we cannot predict secondary structure. A spacer doesn't have secondary structure because a spacer doesn't have reality. Yeah?
So this fourth unit is 1 or 0, depending on whether it's like outside the protein.
Yes.
Okay.
So it should be like when you put on the left, you know,
But wait a minute. Oops. Oh, I'm in the wrong part of my talk now. I got stuck. What do you mean it should be on the left and not the right?
because it's an input, right?
It's an input. So the idea really is, okay, I should possibly draw something around this. This is just to indicate this is a network, and that's how historically it came from. But for the second level here, and the second level really is only that, and I should possibly also recolor it. But for the second level, the input really is that. The output from the first level is the input to the second.
The way it's drawn, we'll assume that like all the red ones are like hidden layers, but actually one of the red ones is
Yeah.
kind of 1 or 0 depending on.
Yeah, and it's also true that, so I have to, so this was done before the era of deep learning. So in some sense, this is sort of exactly doing that before deep learning existed. So this is the, if you want, you can also call it the first time that deep learning was invented. And this slide is in fact from '96. So this is long before this stuff was published. But in those days, this confusion didn't happen. Because deep learning didn't exist. But it's true. I will try to improve that slide. But again,
It looks like it's just a weight, which is learned by several inputs.
thank you for that point. So thank you for that point. In some sense, that sort of predated deep learning. And it's the same concept. It's exactly the same concept. It's exactly the same idea. It's the combination of networks. Except for the big difference here, really, and that is an important difference for CPU and all kinds of other aspects, for the complexity of doing that, they're independently trained units. So this first level network is trained, and then the second level network is trained. That simplifies it in terms of CPU. But now the second level is clear to everybody. Yeah?
So we're interested in this case, for this whole network, now we're interested in predicting this secondary structure of P.
Yes, exactly.
Does it still make sense to have 4 red neurons in the midsection?
No, again, it's not mid. Sorry, the network
Oh yeah, for the input in that case.
instead of?
Because we would never have a spacer at that position, right?
Yes, we will. So again, we will have a spacer. Oh, you mean we will not have a spacer here? Yes, sure. No, that is true.
So we wouldn't need.
That is true. You're right. I could get rid of that spacer. That's in fact the only one I can get rid of. All the others I cannot. But that's the only one I could get rid of. And in fact, this had never occurred to me. It's so much faster to run this without the if.
Or the whole structure doesn't make any sense, probably, but
What did?
why don't you just increase the window by 2?
Oh yeah, no. The windows essentially. I'm not sure whether the next slide says that. No, it doesn't say that. But the ones that I actually used here were 21 or 25. So it was much larger. So why didn't I do more? Because again, it's complicated to draw it.
No, like the thing is, as far as I understand it, right, it's kind of, these are like 3 windows, and like it's just, you have one which predicts like the center protein, and then it's just like then the upper one just predicts the center protein once above, right? And the other one.
Well, so maybe I could have chosen the example differently, but an EEH is something that you, bless you, will not observe very frequently. Maybe the example, so this was again the real example, maybe I should have, for educational purposes, made this HEH or something like that, but the correction could even, even a window of 3 helped. So I tried that.
But like just if it was a window of 3, right? Like just kind of just from the structure, like in this example there, you would have one window which kind of has LVP and predicts V.
But you would see that the E is too short.
And then you would have like VPA and predicts.
No, but you would see that the E is too short, right? Well, no, sorry.
Just for me to understand, you kind of have just 3 windows which predict like a center routine, and they are just kind of one step next to each other.
But again, so if you think about this as a long window of 21, right? And then now you have an opportunity to learn that in a window of 21 you will not observe HEH or something like that. You will not observe HHEE. So there are certain things that within 21 you will not see, and other things that are more likely to see. And that's exactly what this network will learn. So it will bring exactly this correlation that we had to throw away into the system.
But just for me to kind of recap what it's kind of means, like you have like a 3 window, and you wanted to predict in the end.
Think about it as
LVP and predict the signal structure of V. Then you have a window of VPA and predict the signal structure of P. Then you have a window of PAT and predict the signal structure of A. And then use like all these 3 signal structures to predict again the signal structure of P. Right? So that's.
And just now make them longer.
So.
Now make them 21. Make them not 3, but make them not double.
I'm just saying, like, you had like it structured in a way that it would just be one step, would it be just as good probably?
No.
No?
No, absolutely not. So, in fact, it turns out, so one criterion by which you can do that is essentially you ask, on average, the segments, how long are they predicted? And so, in order to produce that result, in fact, you had to go above 20. So until 19, so again on the first level I used 13 at the time, but until 19 you could not really get the number as close to the observed as this one.
No, I'm just saying you have like 3 windows and each is like 21. If you had just one, maybe about 30, might be better.
Oh, so I'm still not entirely clear that I get, but is what you mean that you, instead of sort of moving one window of W through the protein, you have a longer window, and you predict the signal structure for everything in that window? Is that what you mean?
Like this PhD sec thing, which would is just kind of combining 3 different windows, right? If you just had one, it would have probably be better, but it's not the point.
Let's talk about it afterwards. I still don't get it. Yeah?
How is what you just showed different from convolutional neural network? It's a filter, and then
it's not different from convolutional neural network. This is 15 years before the convolutional network.
Oh, but it's the same concept, right?
Well, again, so then I would claim to be the inventor of convolutional networks if I said that, which is not what I'm trying to do here. But it's
Convolutional networks were invented before that time already.
No.
In the 90s, yes.
Yeah, but this was done in the beginning of the 90s. So that No. This was the first time this was done here. So this first time it was published in '92. That is before. Anyway, let's not get into that. But again, so the technical way in which they differ is those are separately trained devices. Okay?
Which is my next question. Why is it better to train them separately instead of...
It's not necessarily better. It has advantages because you can sort of control. In the simplest way, you can say if you don't have enough CPU, then you spend less time. Okay? If you sort of train it together, you spend much more CPU on it. The advantage could be that you control the problem more easily. So one is CPU, another one is control. So the more the parameter space increases, the more things can go wrong. This is not a CPU issue. This is, when you do machine learning, you always have to somehow get a feel for your data. And get a feel for your data may be easier, or is typically easier, for chunks of the problem. That is another possible advantage, yes?
Could you please explain what is the interpretation of the output?
The output is the same as before. So it's the 3 output units HEL. Again, this is predicted secondary structure from the one that uses sequence as input. This is predicted secondary structure from the one that uses secondary structure as input, or predicted secondary structure. The second level here, all it does, it looks at correlations of consecutive residues. Is that clear? Deep learning makes it difficult. And this is sort of a more detailed view of that. And here's an example for convolutionary networks that use that, so that feed the input back into the feed the output back into the input. But all of this is solving many of the issues, segments, beta strands, but still the performance is not much better than 62%. In order to make the 62% somehow much better, we need to put more information into the system. The obvious way of doing that, how can we put more information into the system? And the obvious attempt to do that is make the window longer. Making the window longer doesn't work because it increases or decreases the signal-to-noise ratio. Put differently, by making it longer, you add too many things that for too many of the windows that you learn are irrelevant. And that makes the signal-to-noise ratio go down. That means making it longer doesn't work. So what could work? And I'm not sure. I'm not sure that I want to go down this path here. So I just now decided I will not go down that path. But how could you add more information? Into your method. Again, a longer window doesn't work. And you could try that. It's easy to do, it just doesn't work. What else could you do? How could you put more information into a window of W? Whatever is a good W, making it bigger doesn't work. Yes?
We could compute any kind of feature that might help.
So we could, now he says we could compute features that help. So compute features that could help could be hydrophobicity and the like. True, and it helps somehow. Computing features that could help could also mean you predict other aspects of structure. In the most extreme sense, for instance, you could predict contacts. Context is more complicated as a problem, so we should solve the simpler one first. But there's a variety of features that you can predict that would help indeed. But that is still not really enough. And the solution for this issue is really outside of, this is really specific to the issue. And ultimately, the statement is the following. The statement is that the information is contained in the protein, or it's contained in the evolution, in the following sense. I showed you this graph. I showed you this curve. I told you this is number of residues aligned. When you align two proteins, this is percentage sequence identity. I said if two proteins that are aligned over 100 residues have at least 33 of these residues, 33 of these 100 residues identical, then these two have essentially the similar 3D structure. That means you can change 67 of the 100 residues. That means that there's a lot of variability. That's the way I presented this curve before. But what I didn't present to you, if I go into a lab and I take a protein with 100 residues, I change 5. Just pick, I take these 5 positions and I change the residue that exists there and I put another one in there, another amino acid. Then most of those cases will not lead to a protein that folds. I said a protein put into solvent adopts a unique 3-dimensional structure. But most of those things that I create in the lab this way by changing 5 will just not fold to anything. They will not, in the sense, fold to something that is always the same. They will not adopt unique 3-dimensional structures, so they are not good proteins. In fact, this is also what leads to diseases, misfolding. So when you and your neighbor have some differences in your genomes, a minute part of these, in fact, has problems in the sense that the protein doesn't fold. Now, the reality is that most variations that happen do not, in fact, lead to a protein that works. We don't observe them. Evolution selects against them. What doesn't work doesn't survive. The record that we have, this curve that I show here, is a very exceptional curve. Or this blue region here is something that is created by a selection of the unlikely event, the neutral variant. That means the 67 that are changed in 100 are chosen by evolution to be the rare 67 that you can change. Because evolution had enough time to select all possible neutral changes. Now that means in turn that where exactly those 67 happen, what changes against what, is very informative. There's the entire evolutionary history somehow embedded in that. And this is, for instance, shown in the simplest... So I switched off the microphone. So shown in this slide here, one particular family, the purple ones are more or less entirely conserved columns, of which you have 1, 2, 3, 4 in this particular protein. When you look at the protein, and these are two different views of the same protein, you see that the first residue, first conserved one is here, and the last conserved one is here. Now, if you change something here, that will have an effect on what you observe in this column. Because the protein evolves as a three-dimensional object. Any change at this point here, say that would be a positive and that a negative charge. Say this would suddenly flip by chance, it flip its charge. So it would go from negative to positive. You could recover the interaction by flipping the other one. Okay? And if you did that, then some change that happens here will be reversely seen there. And that's simply because they are connected in 3D space. Okay? Is the idea clear to you? What I'm saying? So it means that if you sort of cut out from this profile, from the 5, say this window here, 5 consecutive residues, in this window of all the possible changes in that family, you have something about what happens somewhere else in the sequence, outside of the window of 5. Because the way this profile looks is affected by what happens on this side, which is away from the 5, right? So you cut out a 5 and you see some reflection of the rest of the protein. It's like a raindrop in which you see somehow the world. Yeah?
Do we need to know this 3D structure?
No, because it works on a 3D structure. And somehow the information about the 3D structure is exactly in that profile. Because when we, for instance, that is one way to predict contacts. We are looking, or connections, distances in 2D information. If we saw that there's a correlated event from here and here, and we suspect that they're correlated because these two, in fact, are close in space. And that, in fact... Say it again? Otherwise, it wouldn't survive in the track record.
It has to be able to fold, otherwise it wouldn't survive.
Yeah.
You can use this prior and then you kind of make
exactly. You see it because it survived, because it's that way. Yes, exactly. And otherwise, it wouldn't be there, so to speak. So if you randomly created a sequence and you put that into that thing, that would violate it. But organisms don't randomly create things. So the moment these profiles will be governed by people who do things in the lab, this situation becomes bad. But as long as they're evolutionarily selected under pressure, that pressure is imprinted upon this. Okay? Now this is the information, the type of information that we want to get at. And that information somehow allows us to simplify the problem, but more simply to put more information into a window of W, whatever the W. And that's what I show in this slide here. So rather than taking, as I initially did, so I take again my 13 consecutive residues out of my sequence, I look at the alignment, so all the family members for those 13, and for some positions like the D here, all family members, or P, all family members have the same amino acid. But then you see for the E, there are already 3 that have an A. And here for the D, there's in fact none of the family members has a D. So now, instead of having a hot encoding, where one is 1 and all the others are 0, I simply put the entire profile in here. So I put the probability, the PSSM, the profile, the position-specific scoring matrix, the thing that tells me that particular D has a different probability than this particular D here. Because here I always observe a D, here I, at least in one case, observe a T. So the profile that goes into this one here is different from the profile that goes into that one. But I do not change anything other than that. I simply replace the hot encoding, the one hot encoding by probability matrix. Clear? There's nothing new. And again, I have the same output, I have the same the same sequence as input. There's nothing changed except for I now use the alignment information as input. The idea is clear. It makes it a little more complicated to sort of get my method. Now I essentially need to begin with a database, so with a sequence, I run against the database, I do this by BLAST, then I have to somehow decide what I put into my alignment by PsyBLAST, and then I put this alignment information from PsyBLAST into the neural network that predicts. Yes?
Because you have then you kind of have not like one specific residual information, kind of have like more like a statistical residual information over like all the aligned sequences, right?
Yes.
So the result always should be checked just like the average.
That's a very important point that you make here. So now it becomes very important how to align my alignment. So what he said is that the moment I do that, I change, he calls it the philosophy of the prediction, which is that rather than predicting for one particular protein, I now predict actually for the family, because I replace the sequence by a probability for a family. That is absolutely right. So now it becomes actually crucial what alignment methods I take. Whether that method that I use has sort of a family-specific view and says I'm not, whatever I align at every single position is the right thing for the family, not for one particular member of the family. In this particular case, you would in fact not predict the secondary structure of a sequence, you would predict the secondary structure of a family. Then there are alignment methods that say, well, my first my query sequence has the highest priority. I do not allow gaps in the query sequence. The query sequence is my reality. For every single residue in my protein, I need to know something because I want to design a drug against that molecule. So for every single residue, I need to know something. So I'm going to have an alignment that has a profile that is sort of subdued to the fact that this has to be a full-length protein without gaps, okay? Which still, in fact, then predicts the secondary structure where my query sequence is only one of many. That's true. You maintain some of the, let's call it binding, or earthing of this is no gaps allowed in my query, but other than that I still replace every residue in that protein by a probability over the family. That's true. It's absolutely true. But now the question really is, does it work? Does it improve the degree to which I predict correctly for one particular family member? This is what I'm going to answer. And obviously the answer is yes, I do very much approve. There's even more information. Now, the one thing, yeah, we have time. The one thing that I want to add here is there is information that I showed you so far, which is information that is local. So I take this W, the sequence out, and I predict for that sequence. So this is the secondary structure for the central residue. And then there is global information. Global information means this is information taken from outside of that, from beyond that W. Whatever W is, now here for instance I look at the composition of amino acids. So is the composition in this particular protein similar to the composition of other proteins, for instance? Or what is the length? Is it an average length protein? Is it a very long protein? And where my window of W with respect to the end of the protein, am I sort of closer to the end or am I somehow in the middle of the protein? If I don't use spacers, you don't have an orientation, right? So no residue is a spacer, so you don't know is it 100 residues away from the beginning or 10 residues. So these are global features. And it turns out that these global features help a lot in the prediction of global aspects of the output. Let me explain that. At some point I showed you slides where I said you have proteins that are all alpha, proteins that are all beta, and proteins that are alpha beta. Now it's a simple classification, right? And the simple classification, it started from Michael Levitt. Michael Levitt in '76 had a publication on that, and he simply said, so this is the percentage of helix, this is, maybe he had it the other way around, I can't remember, and he said, essentially there is a class of proteins that is somewhere up here, I call them all alpha, there's a class that is down here, I call them all beta, so essentially most of the residues, they have a high content of beta, and then there's sort of some cloud alpha beta. How could I predict, so this is, let's call it a three-state model. I have all alpha proteins or beta proteins and mixed proteins. How could I predict that? Well, yeah? Yes, you could train a method. So again, so far we have worked on methods that use per residue prediction. So this one would be a per protein prediction, and I could do one against all. I could actually do the same thing as we had before. But the simplest way in which I can do that, I use the method that I already have. I have a method that predicts per residue helices, and that simply applies these sort of percentages, right? I can, for every single residue of my protein, I can predict whether it's helical and say what fraction of my helices, my residues are predicted to be helical, and then I can classify. Now, this leads to a classification issue. And let me just call it, for simplicity or for clarity, let's call it C3 for classification or protein classification, where I also have a three-state. I have all alpha or beta and mixed. Alpha beta. And I can be right on that or can be wrong on that. Now, there's a Q3, so that's global. And then there's a Q3. Wait a minute. How do I do this? I need a matrix. That's a local score. Q3 is local because it says every single residue, what fraction of the residues are correctly predicted. So in one I measure a fraction of a protein, that protein is all alpha, and one I measure a fraction of correctly predicted residues, that is local. And I just, my head is not screwed on right. I'm not sure how to do this now. So the information in global, in local, in. So I use only local information. And I look at the local in the Q3 and I get some number, whatever the number is. Let's not discuss this. Let's just say 65 and 65. So what I'm saying here is I use global information or I don't use global information, I get exactly the same per residue performance. 65. Okay? That's what I'm trying to say here. I'm sorry for confusing you. Clearly is my mistake. So I'm essentially comparing a device that uses only information from W adjacent residues, that is local in here, versus one that also uses some global information. It is global in the sense that it's outside of the one particular window W. Instead of looking at a particular window of W, it looks at the composition of amino acids in the entire protein. Is that what I call global and local? Is that clear? It's not clear. Okay, so this is my protein. And this is my window. And this window moves through the protein, right? That is if my protein has 100 residues, then I move it 100 times through that thing. What I call local is all the information that is available here. What I call global is all the information in the entire protein. So I look at the local window of W consecutive residues. That is what I talked about before, the 13 times 21 input units. And I add something from what is right and left, or from your perspective, right and left of this W. Namely, for instance, the amino acid composition of the entire protein, which is independent of where this window is here. That will always be, the global information will always be the same. Another aspect that is global will not always be the same is how close to the end is my W. So here my W, I still don't see the spacers, but my W is closer to the end than here. This is a piece of global information, but it will not be the same between these two W positions. Okay? So all of that, I assume, and here again I make exactly this point where I distinguish between one end and the other end. The two ends are distinguished, and this is exactly the point where that matters. And I ask simply, how well do these devices do in terms of predicting per residue performance? And they're absolutely the same. So suggesting, initially when I saw that, it suggested to me that in fact they are the same network. They found the same solution. Then I looked at a global classification problem. Instead of Q3, which is a local measure, because it looks at per residue, I looked at the C3, which is a global measure, because it classifies proteins according to predominantly the entire protein is all helical. And that is not a decision to be made from a single window, right? That decision, the C3 decision, I can only make when I have looked at all the W windows. And then I've added them up, and I've said, okay, I predicted that this protein has no E, and that 30% of the residues predicted, or 40% are helical residues. Now I call it all alpha. That's a global decision. It's not a decision I can make from one W, okay? While every one of these predictions is a decision I make on every window independent, and then I simply sum up these Q3s. And what I saw is that there was this one using the global information was say 65, and this one was 60. So suddenly, and that was statistically absolutely significant, suddenly if I use global input information and I use the global feature to measure the performance, then it paid off. It's a long detour. I was not very clear in the story, but it's a very important part to think about the system. Whenever you look at does a certain feature help, think maybe you should measure it differently. So here, just looking at a local measure, I did not even see a difference. Only looking at a global measure, I found a difference. Yes?
So when you take the distance to the center, for example, so helixes are more likely to be in a certain part?
So the first question that you can ask when you sort of look at differences of the window to the edges, you could ask, is there a statistical signal that the helices, for instance, are closer to the beginning or closer to the middle? None of that actually is true. So there is no simple signal. But for the decision how this window is, whether in that particular constellation of the window, that now means helix or not, that does matter. Anyway, so the important observation here, if you use input information on a different level, see whether you should measure performance on a different level. Yes?
That was one of the global features particularly important. Which one actually made it?
So now we are talking about sort of in detail looking at the features. Those four were equally important. So removing all of those, each one of those had an impact on so they contributed as a sum to this difference of 5 percentage points. I tried many others and they all did not bring an advantage. And so those 4 survived. Later, with more data, this story slightly changed and more global features helped. But the real input here is beyond this field of computational biology, is that if you use input from a different level, so local versus global, whatever for the problem that you will have in reality one day, try to sort of map it in your head. Maybe there's some way in which you can learn from this example. Maybe there is a way in which you can see that it learns or it helps you not for the problem that you're directly going to solve or trying to solve, but maybe there's something around this problem that you can solve through that. Okay, let's get back to the issue here. Now we have 2 levels of network. We use evolutionary information as input. There is one additional issue. I talked about that before. So what this one essentially shows is different networks classifying the points. And say we had, in this particular case here, 4 sort of different networks indicated by these lines in hyperspace. And then the average over the 4 is better than each one of them. And that is the point that I talked about last week, that the error that you make has part of it that is sort of a systematic error, because you don't have enough input, you don't have the right information, and then there's white noise that comes from random choices of the way you initialize the connections, from all kinds of other things. And the more the 2 networks, 2 of these gray lines here, are not correlated, so make different errors, the more averaging helps to get rid of the white noise. That means averaging over many networks helps you. And that in particular is useful, for instance, to average. I said there's an unbalanced and there's a balanced. One is better at predicting beta strand, one is predicting alpha helix, at everything. And the best way to use them both is sort of by averaging. You do all of that, and then you get sort of some additional issues. I don't want to get into that. And then you get to a prediction where we have the observation up here, the 1st generation, 2nd generation, and that would be the 3rd generation. So on average, so here in this particular case, I said this is 50 to 55, so this is better than average. I said this is 60 roundabout, so this is better than average, the 2nd generation. So the question now would be, is this average? And the way to do that, so there's one number, the Q3 is always an average over distribution, where this is the Q3 that I show, and that's the number of proteins, that's the distribution, so 72 is somehow the peak of that distribution. But you also see that there are outliers here. So there are particular proteins for which, in fact, the prediction is much worse than random. If you have a predictor that on average is worse than random, you cannot be worse than random, right? That's clear. Why can the predictor not be worse than random? Because you only predict one? No, I'm not sure that I understand what you're saying. No, but say we have a 3-level prediction, right? HEL. So if you get a method that has 30, say they would be populated equally. We know now is not true. But if each state would have the same probability as the other ones, then the random prediction would be 33%. Now I make a method that is 30, that has a Q3 of 30, which would be technically less than 33. But how can I turn this method that is below random into one that is above random? You swap. As simple as that. If you have anything that is worse than random, any prediction method that is worse than random, you just swap your prediction. You just do the opposite of what the prediction does, and you clearly are going to do better than random. So this is why you can never in practice be worse than random, at least if you know how well you do. You need to know that you're worse than random. Otherwise, of course, you cannot do this trick. But that does not help you here. because the average is 72 somehow, right? So you cannot, if you swapped the performance, your average would go down from 70 to something like 30. So this is a really bad idea. Yes, for these few outliers, your predictions would get better, but for most proteins, the prediction would get worse. So, but at least, how could you possibly hope that you can see for a particular prediction which side of the distribution you are on? Is there any way? So yes, if you know the answer, then you can look it up. But say I have a protein for which I do not know the secondary structure, and I'm the user. You're the developer. You tell me that on average you're 72. Then you show me that distribution. And I'm very scared because my protein could be this one. How do I know?
We like calculate the similarity score to like the most similar proteins tested.
So so we could look up proteins that are very similar in sequence to the one that I'm testing. But if any of the proteins that is similar to the ones that I'm testing is known in terms of structure, I wouldn't do secondary structure prediction, then I would do comparative modeling, right? So I cannot find any protein. So the reason why I apply secondary structure prediction is I have nothing else. And that means there's nothing else that is similar for which I can do that. Okay, so it was a great idea, but it didn't work. No, really, it was a good idea. This is the way you get to ideas. You have to think this through, and without stumbling, you cannot learn to run. Very few at least do. I don't know whether anybody ever did. So, what else could you do? Any idea? Let me look at what my next slide is, because I'm presenting them a little bit out of order. Yeah, the next one is already the solution. So that gets us, yes? That's a great idea, but then you're still random, right? So guessing, so this is still a random guess. So you will tell me, I may be somebody who's very scared of the universe, but calm down, because I don't know, this is 700 proteins or something, I don't have the number here, but this is 1 in 700, so the probability that my protein is this is 1 in 700. That's what you would tell me. But 1 in 700 happens. So it depends really, if 1 in 700 is you die, you're actually scared of it. If so, just go to the subway. If 1 in 700 dies, you're not going to go to, if I tell you today 1 in 700 goes, you will not go to the subway. So it depends on how serious the result is. So no, I'm not, I want something more than that. And the something more than that comes ultimately from, let's just assume we have only a two-state prediction method, H and O. And say for my sample 1, or for my residue I get 0.5 and or 0.6 and 0.4. And for my residue J, I get 0.9 and 0.1. Okay? So that's my output. I have 3 output units, and say these would be the value, and 2 output units in this particular case. So in this particular case, I would say this residue I is predicted to be helix, because helix is the highest number. In this particular case, I would also say it's helix. But you immediately see the difference between the two. This is a much stronger prediction, right? In this particular case, 0.9 of the probability is helix. This is much more reliable that this is a helix predicted than this. This is almost 50-50. Okay? And this is what I try to put into a signal. Refer to the signal as the reliability index. Essentially is sort of scaling that. Just the probability. And what I show here is this reliability index versus performance, per protein performance. And you see that, okay, there are many outliers, but you also see that there is some signal, okay? Proteins with a higher average reliability index tend to be predicted better. And that means here now, in my distribution, I can do more than 1 in 700. The guess that 1 in 700 is going to be this case. I can say, well, if your protein is somewhere down here, you're more likely to be on this side. In this particular case, the big outlier here is not quite the lowest, but it is one on this side and not on that side of the distribution. So I can substantially affect the probability to much more than 1 in 700. I can say this is, I'm not entirely sure how 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's one of the 11 smallest in the whole thing. So if the vast majority is predicted here, so I can almost entirely, so I can quench the fear of the person. If the number is somewhere up here, it's not 1 in 700 but 0. Okay? Is the idea clear? I'm afraid that today I'm not very clear about things. So the idea simply is to use this signal. The signal reflects the strength of the prediction for one particular residue. Now this is completely neutral in the sense, I can use that for any prediction. I don't need an observation for that. I don't need to look up proteins for which I know something. This is simply reflecting how reliable my prediction is. And it's available for every single protein. And this turns out to be one of the features that whenever you use machine learning, you should find a way to use. For SVMs and for many of the packages out there, it's not that easy to sort of squeeze that signal out. But find a way to get it is extremely valuable. Here what this one shows, this is one way of looking at it. That's percentage of residues predicted, that is the per residue accuracy. And if I look at all residues, I never said that. So the method that I now have, the third generation method, does reach a value above 70%. So the simplest version, and there are later versions that go, today we reach over 80% with that, and Michael is going to talk about this. But so this was the first time that clearly 70% was beaten, and this only came through evolutionary information. So for all residues I get, for this earliest version here, I have 72%. If I allow myself to predict only, I look at all the residues that have a reliability of 6 and higher, which is sort of half of all the residues here, 50%, then the performance for those is 85. So for the residues that are more reliably predicted, the half of the residues that are most reliably predicted, this Q3 goes up to 85%. That's a significant improvement, and that allows you to simply focus on what is most likely correctly predicted. Now, let's get back into a few issues here. Let me wrap up in a few minutes the issues of comparisons. So I have in the publication what you see is there's method A that reaches 60%, and method B that reaches 63%. Is method B better? Yes?
Question is 63% what? On all data or yes, I mentioned it.
So this is, I'm not sure, is that what you meant? Yes, so that's the most, thank you very much. This is first should come to your mind. Do they actually mean the same measure? Okay? Very often, I've seen publications that went through reviewing where that in fact was a different number. That's the first question you should ask. What's the second question you should ask?
Is their performance on the same test set?
That's the next important issue. Is it the same data set? It could be. So the most famous example, somebody said that they had some performance of some method, and then I asked them to show me the distribution of that performance. And that person showed me a distribution like this. So where this one here is performance, so increasing performance, and this is distribution, right? And this is the entire curve. If you saw something like that, what would you say? Some people smile and feel it's very obvious. Just say it. Because nobody else seems to, not everybody is sort of finding it obvious, yeah?
I don't think it's a good performance, or it's
It's not a good performance? What do you mean? I never put any value here. How do you know it's not a good performance? So it was, in fact, this whole story started because it was too good. For me, it was too good to be true, and that is why I pushed this person. But the question was, it was a student who asked for him to draw that distribution. It was not I. A student got him to draw that distribution. It was a him. There's no number here, yeah?
Yeah, but like having a high performance is most likely like a statistical outlier. Just like chance from one model.
Yeah, but there are some that are better and some that are worse, yes. Yes? And? That's not really the thing. You guys have all looked at Gaussians. You don't feel that something is missing? Guys, the Gaussian goes on, right? So the student asked, after he saw that, where's this half of the distribution? And the answer was, oh, they are too bad, I throw them away. So this is an extreme case in which you have a certain distribution, and the ones for which your method doesn't work, you throw away, you don't consider, and you publish a score for only the right half where it works, right? This is an extreme way of using a different data set that is very misleading. It may sound funny, but people do that. And again, so it's not just the same number of proteins or the same number of data set, but you really have to have exactly the same data set. And ideally it should also contain all proteins. There should be a cross-validation split. But then the next important issue I asked, well, if all of that would be the case, if it is the same Q3, if it is the same data set, and now the difference of 3 percentage points, does that mean that one method is better? And for that, the next important question is the difference significant? And the difference significant is a statistical issue. So that ultimately gets back to this question, how wide is the distribution here? And the width of that distribution leads to a standard error. And that standard error essentially defines how much of a difference you should be at least 2 standard errors away from the difference.